Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about Ramsey theory. Here's a very simple example from Ramsey theory, a classic problem about friends and enemies in a group of people. Suppose there are 6 people in a group, and every pair of them is either friends or enemies with each other. Show that in any group of 6 people with this property, there is either 3 people that are all friends or 3 that are all mutual enemies. The way we can model this is as a 2-colored graph. So you have 6 people here drawn as vertices of a graph, and we color the edges of K6 either white or dashed yellow. If they're white, then that means they're friends. If it's dashed yellow, that means those 2 people are enemies. So in this 2-colored graph, can we find a monochromatic triangle, meaning 3 people that are all either mutually friends, like this triangle, or are all mutual enemies, like this triangle? In this case, there's both. It turns out there always has to be at least one of them. And let's see why. So to prove this, let's consider one person, which we'll call V for vertex, and let's consider all of the edges coming out of V. So V is connected to 5 other people with white or yellow dotted edges, and of these 5 edges, by the pigeonhole principle, since they're colored in 2 colors, some color must have 3 of the edges, at least 3. So there's either 3 people that V are friends with or 3 enemies. In this case, we've drawn it so that there are 3 friends. So let's consider these 3 friends of V. Now, if any of those were friends with each other, then you would have a triangle with V. And so that means that these people must not be friends with each other, so they must all be enemies. But then that means we have a triangle of enemies. And so if there's 3 friends of V, then those must be enemies. And conversely, if there's 3 enemies that V have, those enemies must all be friends with each other. Otherwise, we do get a triangle. And so in any way we try to do it, in any way we try to avoid a triangle, we are always forced into having a triangle in the end. Now let's try to generalize this. An m-clique in a graph is a subgraph isomorphic to Km. So in the previous problem, we were looking for 3 cliques of a certain color. 3 clique is just a triangle, whereas a 4 clique is a copy of a K4 within your graph, meaning 4 dots that are all mutually connected. Maybe we want all 4 to be mutually friends, or all 4 mutually enemies. And a 5 clique is 5 dots that are all mutually connected, and so on. So here's a Ramsey number. A Ramsey number, RMK, is the smallest n such that any 2-colored complete graph Kn has either a monochromatic m-clique in the first color or a monochromatic k-clique in the second color. So for example, R of 3, 3 is 6. As we showed on the previous example, if we have a 2-colored K6 colored white or dashed yellow, then there's either a white 3-clique or a yellow 3-clique. So either a white triangle or a yellow triangle. And now let's see some other Ramsey numbers. If you have 1 and n, so if you're either looking for a 1 clique, which is just a point, or an n clique, well, if we just want a 1 clique, all we need is 1 point, and it doesn't matter what the colors are. So actually 1 is the Ramsey number of 1, n for any n. But for 2 and n, well, a 2 clique is an edge, right? It's 2 vertices that are all mutually connected. So if we're looking for either a white 2 clique, meaning a white edge, or a yellow n clique, well, if we have at least n vertices, let's say we have an n vertex graph, and we color everything white or yellow, well, either we color it all yellow, in which case we do have an n clique, or we have at least 1 white edge, in which case we have a white 2 clique. And so we have that n is sufficient for that. Now, we haven't proven that we can't get anything less than n, but if we think about it, if we have n minus 1 vertices, then you can have them all colored yellow, and that would avoid both possibilities. Similarly, we haven't actually showed that R3, 3 is not 5, that 6 is actually the minimum. But you can show this in the Now You Try at the end of this video. Finally, we have a symmetry. R of m comma k equals R of k comma m, because this just involves switching the colors, and the problem becomes the same thing. Here's the table of known Ramsey numbers so far, up to 6. Here's the table of RNM for n going across and m going down. So you see it's symmetric, first of all, because we have the symmetry we talked about. We have 1s along the first row and first column, because if you have R of 1 comma anything, it's 1. R of 2 comma anything is itself, so these numbers are 2, 3, 4, 5, 6, etc. And after that, it gets quite difficult. So R of 3 comma n goes 1, 3, 6, 9, 14, 18. And then R of 4 comma n is only known up to n equals 5. So we have 1, 4, 9, 18, 25, and then we don't know what the Ramsey number R of 4, 6 is. So there have been computer calculations and papers written on this, and we know whatever it is, the question mark, it's somewhere in the range between 36 and 40. You need that many dots to guarantee that you'll either have a monochromatic 4 clique of the first color or a monochromatic 6 clique of the second color. Similarly, we don't know what R of 5, 5 is. It's somewhere in the range of 43 to 46. We don't know what R of 5, 6 is. That's somewhere between 59 and 85. And then the Ramsey number R of 6, 6 is somewhere between 102 and 160, and nobody knows exactly what the number is. But the number has to exist. There's a theorem that Ramsey numbers are always finite, so they're always bounded. But these bounds get bigger and bigger as things go on, and it's very hard to compute Ramsey numbers exactly in general. So now you try. Find a 2 coloring of the edges of K5 that has no monochromatic 3 clique. This will prove that R of 3, 3 equals 6 and not 5. And that's all for today, and I'll see you next time.